Hi, good afternoon, everyone. I just want to know that you can hear me well. Okay, good. So we will start today's lecture on nanomaterial behavior in the aquatic environment. So when we think about nanomaterials in the aquatic environment and a snapshot, there are actually many topics that are relevant to this. One issue are the main sources for nanoparticles. Another one are the physicochemical properties of the nanoparticles. Then we have the transformation processes. Also, chemical transformations, physical transformations, biological transformations, and these things were discussed in the morning with the Dr. Ram, and I'll also present a few issues related to that. Then another very important topic on the interaction of nanoparticles with the aquatic environment relates to the toxicity of nanoparticles, okay? So there are various topics, for example, the factors that affect the toxicity, and then also there are issues related to non-interactions and the effect of dissolved organic matter on the aquatic environment, and then enhancing the toxicity due to the presence and absorption of DOM to the nanoparticles. And again, there's also other interactions that relate to photocatalytic properties of nanoparticles and how that can also impact toxicity. When we look at that classification of nanoparticles, and this was also discussed in the previous lectures, we can classify as natural or anthropogenic. So these are the natural nanoparticles, and these are the anthropogenic nanoparticles. The anthropogenic nanoparticles can be also classified as engineered nanoparticles and incidental nanoparticles. Example for natural nanoparticles include, for example, combustion products, soil erosion, also, for example, forest fires and volcanic ash, ocean spray. So all these are considered natural nanoparticles. Now, incidental nanoparticles are actually byproducts of human activities. So they can, for example, relate to burning fossil fuels. Also from vehicle exhaust, there's release of these incidental nanoparticles and mining processes. They are actually characterized by poorly controlled size and shape because they are incidental. And also they may be a mixture of different elements. Now, one of the most important classes are the engineered nanoparticles. And these engineered nanoparticles could be, for example, polymeric, organic or inorganic nanoparticles. And they are actually specifically designed and deliberately synthesized by humans. So most of these nanoparticles are present in the environment and a result of human activities, mainly from industrial production. This paper, for example, and many others actually show, for example, the use, properties, and transformation and toxicity of nanoparticles in the aquatic environment, and we will discuss these factors. When we look at the physico-chemical properties of nanoparticles, we also discussed this. One of the key parameters are the particle size and the surface area. The small size of nanoparticles inhibit their gravitational settings, okay? And therefore the particles remain suspended in their environment matrix, such as air and water. These nanoparticles can only settle down if they aggregate with other particles or within themselves. And it's also known is that when the specific surface area increases, the particle size decreases. Okay, so this is one important feature. Another important feature that we discussed yesterday was the surface charge and degree of agglomeration. And we know that the surface charge is represented by the zeta potential. So the zeta potential is also a key parameter in understanding nanoparticles in the aquatic environment. And the surface charge controls the stability of the nanoparticles, which impacts, of course, the agglomeration of these particles and also the toxicity. So again, when looking at nanoparticles in the aquatic environment, we look at the particle size and surface area, specific charge and degree of agglomeration, which also has an impact on the toxicity of those particles, which we will discuss soon. Then there's also issues with particle morphology, so we can see the spheres, cubes, rods, and so on. Also, surface coating is an important parameter because it can actually eliminate or induce toxicity. Also, Dr. Ram spoke about this in the morning about the issue of the surface coating. And this depends on the nature of the coating used. Another issue is the particle composition and the crystalline structure. So for example, rutile titanium dioxide induces toxicity, while Anata's titanium dioxide nanoparticles did not show this type of toxicity. So also the crystalline structure of the nanoparticle is very important in understanding its toxicity. Then another important feature are the materials. Okay, so for example, with personal care products, sunscreens, and cosmetic products, they contain zinc oxide and titanium dioxide. So these nanoparticles are subjected to different alterations in water. Therefore, when they reach water, they can be subjected to alterations. And this can result or enhance their dispersion in the aquatic environment. And nanoparticles can also be incorporated into the sediments, and they can also dissolve. So it really depends on what's happening. For example, in wastewater, engineered nanoparticles such as silver nanoparticle, for example, they were found in waste of laundry, okay, in wastewater that comes from laundry and clothes washing. And the pathways for these nanoparticles are influenced by the transport, as was discussed in the morning, but also by the transformation that can happen when there's interaction of these particles with wastewater constituents. So these particles can either absorb to sludge, for example, or they can form agglomerates, and this will actually increase or decrease their reactivity. Therefore, the complexity is very high. There's also issues with anti-fouling applications. For example, nanoparticles are added into paints, such as carbon nanotube materials, and they were recently found in biofouling prevention. So the nanoparticles can be used to prevent a biofouling, which is, of course, biofouling occurs, and we will discuss about biofouling tomorrow, but it is actually the unwanted deposition of microorganisms on surfaces. And actually biofouling occurs always when we have a surface microorganisms in aquatic environment. So these factors are all important. So just to remind a little bit about the zeta potential and how we measure it. So we know that, just a quick reminder, this is our solid particle, this is the stern layer, okay? And this is the shear plane. So the shear plane is actually the difference, so the zeta potential is actually the difference between the dispersion media, okay, between the potential of the dispersion media to the potential of the shear plane. Okay, so this is the zeta potential. And Okay, yeah, I think so. We kind of discussed this, but this parameter is extremely important. And this only occurs, again, in the aquatic environment. So when the nanoparticles are actually present in contact in liquid, then we exert a zeta potential. And it's a key element of the stability of colloids, as we discussed also yesterday. The zeta, also we discussed yesterday, if the zeta potential is higher than minus or plus 30, then we can consider the suspension as stable. Okay, so we'll have a stable dispersion. And if the zeta potential is between minus 30 to plus 30, then we can have different phenomena as aggregation, sedimentation, and flocculation. So again, the zeta potential is measured in the shear plane, okay, in this plane here. And again, when we look at the charge formation, we can have a charge formation at the solid-liquid interface for hydrophilic material surface with acidic or basic functional groups. So we can have your acidic or basic functional groups. And another formation of surface charge could be due to hydrophobic material surface without even functional groups. So we can have your hydrophobic interactions. And the pH value, which the zeta potential is 0. So the pH value, for example, here, which the zeta potential is 0, is also called the isoelectric point. So all these actual measurements and parameters are very important in characterizing nanoparticles. I don't know if I'll go over this. Well, the accumulation of nanoparticles are actually due to, as we said, mostly due to human-based interventions. And these aquatic engineering nanoparticles, they actually enter from different sources. It could be also from non-point source and point sources. So I'll go over this. I don't want to waste time on this. Also, just a little bit discuss about the transformation processes. So as also said in the morning, the transformation processes are either physical, right, chemical, and also biological. So these are the three basic or main transformation processes that actually define the behavior of nanoparticles in the aquatic environment. Okay. Also, another important parameter is the redox. Redox is actually okay, if we have, for example, an oxidizing environment that is rich with oxygen, for example, with aerated salts or aerated natural water, okay? Or also the reductive environment, and also this was discussed in the morning, which is actually depleted of oxygen, such as groundwater. So surface water will tend to have more dissolved oxygen compared to groundwater. Why is this important? Because when we have an ORP, so an ORP is actually the measurement of the oxidative reduction potential. So when we have an ORP that is negative and that enhances the dissolution of natural nanoparticles into the aquatic environment, for example, this can happen when this is a phenomenon that happened in Israel when effluent that underwent a secondary treatment was infiltrated into the groundwater through a process that is called soil aquifer treatment. Now, due to the non-oxidative properties of this effluent, because it didn't contain oxygen, actually it resulted in dissolution of manganese and iron oxides from the soil, which was a mixture of clayey sand soil, and the manganese and iron that was actually dissolved from the natural rock to the effluent went to agriculture irrigation in the south of Israel. Now, what happened is that when these iron and manganese that was dissolved in the ionic form, when it reached the drip systems, it resulted again, the oxygen, the interaction of oxygen in the drip irrigation systems resulted in formation of oxide. And these oxide clogged the drip irrigation systems. So we can see how everything is kind of like connected through having redox conditions that result in dissolution, through again reoxidation due to the presence of oxygen and formation of particles and oxide that can clog the systems. Now, one of the solutions, of course, is to add oxygen to the effluent and therefore decrease the dissolution. What we did is, and we'll talk about these processes later, what we did, we ozonated the effluent because we wanted also to add oxygen and also to degrade the micropollutants. And the reason is that we had also presence of micropollutants. So we wanted to have two things happening at once, degradation of the micropollutants and rendering them more biodegradable. And also, in addition to that, we wanted to add oxygen to the effluent in order to result in, or to control the dissolution of iron and manganese inside the water, in order to avoid formation of iron and manganese oxides, nanoparticulate oxides for that case. Yeah, so this, for example, is a process that shows how these oxidative reductive processes in redox are very important. Soft metal cations. So for example, soft metal cations, it could be zinc and copper. These are nanoparticles that actually can also dissolve in the water. And that can, and the toxicity actually decrease due to the reduced surface area of the nanoparticles. But again, these are complex phenomena, and we're not sure like how and what would be the magnitude of the dissolution and how it will impact the toxicity. So these are things that are actually very important. Now, just to summarize also what you learned in the morning, the possible transformation processes of engineered nanoparticles. So we can have here like different phenomena occurring. For example, sedimentation. So sedimentation is governed by Stoke's law. I'm sure you learned about that. Stoke law is actually a mathematical representation that expresses the drag force that is resisting the fall of small particles into a fluid medium. Now, since our fluid medium is water, then we actually consider the drag of these particles as they fall or try to sediment inside natural water. However, since gravity force is regulated by Stoke law, and we know that these particles are diffuse and they don't tend to settle unless they agglomerate. Another important feature is the absorption of inorganic and organic ligands and macromolecules on the nanoparticle, and that can actually significantly change the surface charge of these particles. And we know that in natural water, we do have all these dissolved constituents that can result in actually changing the behavior of those nanoparticles. Another issue could be sulfidation of soft metals that induce their aggregation due to formation of insoluble metal sulfides, okay? And we can also have dissolution of to the production of partially soluble metal oxides. So all these phenomena can occur with engineered nanoparticles. Now, the topics that we will emphasize today are nanotoxicity, mechanisms for nanoparticle toxicity, ecotoxicity, genotoxicity, characterization, and challenges and remedies. So just stop a second. I want to know if you have any questions. If not, we will continue. Okay, so let's continue. Okay, so these topics are important in understanding the nanomaterial behavior in the aquatic environment. Okay, so so when we look at the effects of nanoparticles in the aquatic environment, there are many things to consider. One of the main things is that due to the interconnectedness of the aquatic ecosystem through the marine and also the atmospheric transport routes, the aquatic ecosystem are vulnerable, very vulnerable to nanomaterial pollution. So this is one major thing that is very important to consider. Also, the anthropogenic contamination that is derived from human activity. So we discussed that human activity results in this type of pollution. Result in rapid increase of for example, carcinogens in the natural habitat. And this actually results in stress, and pressure on the natural habitat and the animals and the aquatic life that exists within this habitat. Also, the concentrations of the nanomaterials or the nanopollutants also have an impact on the human on the habitat. So it's also due to the interconnectedness, due to the anthropogenic contamination, there's also issues with the concentration. In addition to that, the EU has found more than 100,000 substances that could end up in the environment and cause a threat to aquatic life. So this thing is very prevalent. And if we look at figure 2, for example, so the y-axis is the number of studies on pollution and cancer, and the x-axis is the number of studies on cancer. And what we actually see from this figure is actually the number of studies that indicate cancer in the aquatic environment, and the number of these studies that link cancer to pollution. So there are less studies that link the cancer of the aquatic environment to the actual pollution. And this is, of course, troubling in a sense. So this is one thing to be aware of. And in addition to that, if we look at the different organisms, we can see here that mainly in fish, most of the studies were done in fish. Okay, so these are fish, but there's also mammals. So this represents the mammals. And then this represents the birds and the reptiles. And then we have, for example, the flatworm and all these types of organisms, okay? So this is a very important feature. Another important feature is that the toxicity of nanoparticles in biological media can also cause damage to the genetic material. So actually, DNA is a significant cellular component that is very susceptible to oxidative stress. So oxidative stress that is actually induced by the presence of nanoparticles in the aquatic environment can also result in DNA alteration. So this is like a huge impact that, of course, must be considered when we want to understand the nanomaterial behavior in the aquatic environment. So let's discuss a little bit about toxicity mechanisms. And here are actual examples of how nanomaterial interact with living organisms through the nanobio interface, okay? So there can be, for example, uptake and distribution of nanomaterials. This is illustrated in the Daphnia in A. And we can have very different phenomena, for example, adsorption on different components of the Daphnia. through a dietary way, through the gut, and we can have also through the through the anus from the water phase, adsorption on different components. So all these issues are very important, and nanomaterials are discarded into the aquatic environment. They can enter this environment, as we discussed, either as themselves or as aggregates or as soluble ions. So they can be in these three different forms. It of course depends on the conditions and the type of the nanoparticles. And all these processes, transport and transformation processes that govern the actual state of these nanoparticles will impact their behavior. So these are important things to consider. For example, in wastewater, as we said, nanomaterials can absorb to sludge and form agglomerates with organic matter. Nanomaterials can actually penetrate the cell membranes of organisms and bind to different cellular organelles. And this can, for example, result in disruption and form bioconjugates with the DNA. Nanobio interactions are really complex to understand. So I'm not an expert in toxicity in any way. Also another very important phenomena that I read about is about it's called protein coronas. So protein coronas, actually, they play an important role in determining the fate and behavior of these of nanomaterials in biological environments. The protein corona or the PC, the protein corona or the PC is a critical role in making the particles easily recognized by innate immune system. So the interaction of the nanoparticles with the corona proteins will actually result in can result in these particles interaction due to the fact that they will be easily recognized by the immune system. Okay, so this is one important thing. In addition to that, it can result in denaturation of proteins, like we saw also with the DNA, a disruption of the DNA. We can also have the denaturation of proteins. And impact on biocatalytic processes. So all these things are actually occurring. It's of course very complex. And the formation of nanomaterial protein corona is actually hydrodynamically associated with the physical chemical properties of the nanomaterials, of course, and the adsorption mechanisms. So the idea is that in entropy-driven binding, which means, is it favorable binding or not? So if the binding is favorable between the nanoparticles and the proteins, this can result in all these phenomena, as we said, as protein denaturation, or it can result in actually the nanoparticles attaching to this protein coronas, and they will be actually recognized by the immune system. These things are very important. We can also see that with B and C, B is the interaction between nanomaterials and cell membranes. So we can see different types of interactions. So it can be through hydrogen bonding, electrostatic attraction. It could be through hydrophobic interaction, receptor ligand interaction, and also these can result in ion release. So all these things can happen. Now, the toxicity mechanism, when we look at the toxicity mechanism, there are different types of mechanisms that we need to actually look at. One of them is oxidative stress. Another one is ecotoxicity. The third mechanism is genotoxicity, okay? So looking at these three mechanisms, oxidative stress, ecotoxicity, and genotoxicity. So just to make it very short, oxidative stress is a type of imbalance. It's actually an imbalance between the production of ROS. So ROS are all the reactive oxidative species. And we will discuss this also when we will discuss interaction of nanoparticles with ozonation, hydrogen peroxide, and these type of engineering-based systems. But this also happens with natural cells. And this imbalance results due to the high concentration of ROS, and due to the ability of the cells to reduce the ROS. And therefore, if we have overproduction of reactive oxygen species, more than the cell itself is able to balance, then we have oxidative stress, okay? And this oxidative stress results in the fact that the cell cannot maintain its natural physiological redox regulated functions, okay? So this is a very important issue. As we said before, these oxidative stress can result in oxidation of protein and result in protein radicals. So with radicals, we have usually chain reactions. So if we generate an reactive oxygen species, for example, hydroxyl radical, the hydroxyl radical can in turn oxidize the proteins and result in a chain reaction. So we can also have initiation of lipid peroxidation. Lipid peroxidation is also an interaction of the radicals with the lipids. And also we can have DNA strand breaks and modification of the nucleic acid. We can have a change in the gene expression. We actually did a study a few years ago where we took up Pseudomonas aeruginosa bacteria, and we actually sequenced all the different genes, and then we wanted to understand which gene was upregulated due to exposure of hydroxyl radical that was generated through the process of UV combined with hydrogen peroxide using a low pressure lamp. And so we were able to target the gene that was upregulated, and we wanted to use it as a marker, as a biomarker for understanding when we have oxidative external oxidative phenomena that are actually impacting the intracellular components of microbial cells. We never managed to develop the sensor, but the idea is that measuring these oxidative processes is very complex, especially if we want to measure the impact of the oxidative of these oxidative processes in the aquatic environment inside microbial cells. The idea that we wanted to do that is that Pseudomonas aeruginosa is a bacteria that is known to form biofilms. So we wanted actually to connect between the gene expression due to the oxidative stress in the water to the formation of biofilms. That was like a huge target, or I would say mission, but we did manage to find the responsible gene, and we never, I think we submitted a proposal, but we never worked on it. We never continued to further work on it. But if we can target, for example, genes that are expressed due to oxidative stress that the water imposes on these microorganisms, then we can actually translate that to engineering as well. Of course, I'm not talking about higher organisms. Higher organisms are much more complex than bacteria. Okay, so, as engineers, we try to look at how we can take things and simplify them to understand design of systems. And I think also Dr. Ram also discussed about this yesterday very nicely about how we use nanoparticles in order to design and how to smartly design systems, looking at both treatment, looking at fouling formation, and looking at all these things. So these are all, so if we can link the factors, these basic factors with engineering, it makes it very interesting. So as I said, the first thing is the oxidative stress that the nanoparticles impose on the aquatic environment and the microorganisms. And so when we have hydroxyl radicals, it can result in protein oxidation, DNA strand breaks, enzyme and activation, and lipid peroxidation. Okay, we can also impose Fenton reactions. Okay, so we can impose Fenton reactions that are actually prevalent at very low pH. Okay, and the presence of Fenton reactions can also result in formation of superoxide dismutase, which is an enzyme that actually is generated in situ inside the microbial cells upon exposure to superoxide radical. And the superoxide radical can also be generated, of course, due to these different phenomena. Then we can have also in situ, we can have also the oxygen can form superoxide radicals, which will result in release of SOD, which will transform this to hydrogen peroxide. And we can also have hydrogen peroxide if it's generated in the water. It can also diffuse inside microbial cells. So one thing that I learned to differentiate is between the oxidative phenomena that are happening in the aquatic environment and those that are happening in situ inside the microbial cells. Okay, because we, for example, can form hydroxyl radicals ex situ in the water, or they can actually be formed inside the microbial cells. The same with superoxide radicals, same with superoxide anions. We can form the superoxide in the water, and we can also have in situ generation of superoxide inside microbial cells. Just maybe one also interesting thing that we found with superoxide radicals is that we wanted to actually measure or the impact of UV irradiation in water disinfection on microorganisms. And we took bacteria that had a plasmid that actually resulted in either increase or decrease of stress genes. And that way we were able to target which gene is actually upregulated due to the stress that we imposed on the water. And in that case, the stress was UV photons in wavelengths between 250 to 300 nanometers. And when we impose this oxidative stress, it is well known that UV absorbs in the DNA of microorganisms and result in and will impact the reproduction of those microorganisms through thymine dimer formation. And what we saw very interesting is that we saw that we also form superoxide radicals inside the microbial cells when we impose the microorganisms to UV disinfection. And this was the first time that this mechanism was actually found. And why is it important? Because when we know like the mechanisms, we can actually target the mechanisms for engineering-based disinfection types. So all these things actually connect. And I think our goal, since the 3 lectures in this course come from environmental chemical engineering background, we are not material engineers, but we take the knowledge from the material engineers and translate that into improving treatment of water, wastewater, and reuse. Okay, so so we talked about the oxidative stress, and then there's also the issue of the ecotoxicity. Okay, I think we discussed that nanoparticles can be toxic to the different organisms, and also some of the membranes are permeable, which means that some of the contaminants can actually permeate through the membranes, while others may not permeate through the membranes. So these semi-permeable membranes are actually also impact if the reactions are surface reactions or inside the cells. And then another issue is also the genotoxicity. And this results in damage to genetic material. Okay, so again, as we said, the genotoxicity can directly damage the DNA, okay, due to interaction with the nanoparticles. So I would say that is the important feature. Oh, so the toxicity mechanisms, the factors that impact toxicity mechanisms are aggregation, dissolution, surface charge, reactive oxygen species, and also the shape of the nanoparticles. So as I showed in the previous slide, overproduction of ROS, okay, reactive oxygen species, will result in oxidative stress, okay, that is induced by the nanoparticles or the nanomaterials. And this leads to nanotoxicity. So again, I'll just repeat this. Overproduction of ROS, okay, of reactive oxygen species, can result in oxidative stress. This oxidative stress that is induced by these nanomaterials is a predominant mechanism of nanotoxicity. Okay, so this is one of the dominant mechanisms of this toxicity. In addition to that, there is oxidative DNA damage, okay? And this oxidative DNA damage is associated with mutagenesis. It's also with carcinogenesis and aging related to living organisms. So it could be mutagenic, carcinogenic, or result in aging. Okay, so all the oxidative DNA damages result in all these phenomena. Also, nanoparticle surface coating can promote also genotoxicity. And also other different important parameters are the charge, the shape of the particles, the charge of the particles. And this can, and the ability again to generate reactive oxygen species. Okay, so all these things are important. Now, when we have interaction, for example, there was a study that found interaction between supermagnetic magnetite nanoparticles. Okay, so they were magnetic nanoparticles. It actually resulted in change in the interaction of those particles with the lipid resulted in change in the lipid transition temperature. And this resulted in increase in the membrane fluidity. So for example, this is an example of how this interaction affects the membranes. Also, as said before, there can be impact on the nucleic acid by direct interaction with the DNA, okay? So for example, if we look at this image, we can have electrostatic interaction with the bacteria wall. We can have formation of reactive oxygen species. So we can see your formation of hydroxyl radicals, superoxide radical anion, hydrogen peroxide, for example. So we can have generation of all these reactive species. This reactive species will actually oxidize either the membrane, or if they are formed inside the cell, they will oxidize different components of the cells, okay? So all these things can happen simultaneously. But this topic is extremely complex. Okay, so natural organic matter has a huge role in toxicity mechanisms. Okay, so natural organic matter that is present in water. So for example, we can have in surface water few ppms of NOM. In effluent, wastewater effluent, we can have maybe like 10 to 15 milligrams per liter of natural organic matter. So this natural organic matter can actually has an important role in the nanoparticles and the interaction of the nanoparticles with toxicity. So one thing is that it can result in suspension stabilization change. After having interaction of the nanoparticle with the NOM, the natural organic matter. For example, a study showed that metallic nanoparticles aggregates were broken down. And that results, of course, in a much lower hydrodynamic diameter compared to the aggregate, obviously. This also increased the stabilization of the suspended metallic nanoparticle. And due to this stability, the nanoparticle hydraulic residence time or suspension in the water, of course, increased. So the stable nanoparticles had a higher residence time because they were stable and they were dispersed in the water. Because they were dispersed in the water, transport and transformation phenomena could occur, okay? And that result in impact on the free-swimming microorganisms. So you can see how these phenomena are very complex. And also it resulted in exposure to the floating and swimming organisms, and also while decreasing their availability in benthonic organisms. And these are organisms that live on the seafloor. So if we have phenomena that induce the breakage of the aggregates, then the suspended nanoparticles will mostly impact the free-swimming organisms and less impact the animals that live on the seafloor. So this is one phenomena that is related to a suspension stabilization change. Another one is the bioavailability of metal ions that are dissolved. Okay, so we discussed a little bit about the dissolution of these things. So for example, this is actually very specific to soluble metallic nanomaterials. So the soluble metallic nanomaterials have an impact on their bioavailability depending on the state of the material. So for example, zinc oxide, the toxicity of soluble metallic nanoparticles, for example, silver and zinc oxide, is partially contributed to the release of the metal ions. Okay, and actually it was found that fulvic acid, the presence of fulvic acid in the aquatic environment, resulted in an increase of dissolution. Yes, it resulted in increase of dissolution of these type of metallic nanoparticles, and this actually explained the enhanced toxicity of the copper oxide metallic nanomaterials by fulvic acid. Okay, so fulvic acid resulted in dissolution of copper ions, and this actually impacted the increase in the toxicity of those nanoparticles. So this is, for example, another impact of natural organic matter on the toxicity. Another thing is so we discussed the bioavailability, and another thing is also related to the electrostatic interactions, and we discussed the electrostatic interactions. So for example, if we have an E. coli with a negative charge, for example, E. coli have a negative charge below -30, okay? So usually, which means they're pretty stable, right? We said that if the zeta potential is below -30, it means that the particle is stable, that occurs at about natural pH, okay? So it's very important to state the charge and also the pH that is related to that charge, okay? And what happened is that The electrostatic interaction is also very important in toxicity, okay? Because the electrostatic interaction of, for example, metallic nanoparticles in organisms is impacted by the zeta potential of the organisms and the charge of the nanoparticles. And the NOM or other ions can, or NOM or macromolecules or other ions can actually serve as a bridge even between nanoparticles and biological organisms of the same charge. So I showed you yesterday that, for example, when we coated ceramic membranes with N-doped titanium dioxide, and we wanted actually to do that in order to disinfect viruses in water. But what happened is that the viruses, instead of being inactivated, because when we coat a membrane with N-doped titanium dioxide and we expose it to solar radiation, we form hydroxyl radicals. Now, we wanted the hydroxyl radicals actually to oxidize the virus exterior components, okay? But what happened is that we had calcium in the water, and the calcium actually served as a bridge between the membrane and the virus. So the viruses were actually disappeared from the water, even in dark conditions without exposure to solar radiation. And we were puzzled. We repeated the experiments again and again and again and again because we didn't expect this. And what we saw is that even in the dark, all the viruses disappeared from the water. And then we understood that it's related to the calcium. And so then we did many tests with a streaming potential to understand how calcium at different concentrations absorb to the ceramic-based titanium dioxide membranes. And so we can also take this understanding that we're learning about toxicity also to engineering design. So this is also another important point. And also there's an issue of steric repulsion, okay? So the nanotoxicity often starts at the direct contact of the cells and organisms with metallic nanoparticles. So it has to have like direct contact, okay? Although, as we showed before, dissolved ions can result in adverse effects. So we can result in dissolved ions, and that depends on the conditions that that these nanoparticles are being exposed to. Okay, so for example, we showed before that fulvic acid can result in dissolution of copper oxide to release copper 6-fold. So therefore, the organic matter in the water can result in enhanced dissolution of metallic nanoparticles, which will impact or not the toxicity. So for example, with copper ions, the impact of the copper ions on the toxicity is much higher than the nanoparticle itself. So even if we have steric hindrance, still dissolution of metal ions from these particles can result in dissolution of ions that will have an impact on the microbial cells. So this is also another very important phenomena. So it's not only the physical interaction, but if we talk about physical interaction, then usually we talk about membrane damage, okay? So if we have interaction of the nanoparticles with the membrane, that can result in membrane damage through disruption of various processes and phenomena like we discussed that could be inside the cell. So if we look at this picture, we see here the first phenomena that we discussed is suspension stabilization, okay? Then the second phenomena is altered bioavailable of metal ions, okay? Then the third phenomena is electrostatic repulsion, okay? And then the fourth one is steric hindrance. And then we have also Ross generation. So all these things can actually impact the interactions that are external to the microbial cell, but they can also result in cascade reactions inside the cells. Okay, so the ROS-mediated damages that are a cascade reaction inside the cells can also result in DNA damage, in membrane damage, and dysfunction, or these phenomena can also occur external to the organisms. Okay, so just remember that when we talk about these mechanisms, all these things can happen. Yes, so this is very important. I want to go over, I plan to talk more. I want to go over one more slide before I want to see if there's any questions. So this is nano silver. Let's talk a little bit about the global market, okay? Because we are talking about nanomaterial behavior in the aquatic environment. Keep the nano silver source. Let's think about the global market, because with all the nanoparticles that I've examined for this course, there is a rise in the production of all the different types of nanoparticles in the market. So what will happen? Of course, they will reach the aquatic environment, because the environmental philosophy shows that everything that is generated will reach eventually the environment. Okay, so this is like a thing that we must take as a given. So the global silver okay, we don't have so much time, but the global not go to silver. So the global silver nanoparticle market is valued at $1.8 billion. That was in 2019. And projected to reach more than $5.5 billion in 2027. More than $5.5 billion in 2027. Now, just remember that the companies that manufacture these nanoparticles, they are not accountable for the environmental damage. This is also a given. The pollutant does not pay, and the environment pays, and all the aquatic organisms and with humans, but that is also something that is given. And usually this production is in the electrical and electronics industry, but also silver. Silver has a high electrical and thermal conductivity. So we know that silver has these characteristics, and that's why it's being widely used as a consumer product, okay? Either as a paste and ink or as an adhesive. So nano silver is everywhere. Also in medical processes, and even, you will not maybe believe, but maybe you know all this, from textiles, there's also release of silver nanoparticles into the environment. And the direct, also even by washing, washing in the aquatic environment can result in release of these particles. So we can see here also, for example, interaction of silver nanoparticles with proteins to form silver protein composites. From textiles, we have release of silver nanoparticles, also from different chemicals, and also, of course, in detergents, shampoos, toothpaste, face mask, and medical. And also medical clothing, all these actually have silver nanoparticles. And again, this impacts the stability of the protein corona formation. And in addition to that, it actually will just increase. It will only increase because of the demand in the electrical and electronics industry. So I will stop here. I hope you're surviving this lecture. I did not reach the point that I wanted to, so we will continue to discussing that toxicity tomorrow. But if anyone has any questions, I hope what you got and understood that there's huge complexity. that is external to the cell or internal into the cell, and different phenomena happen. The fate and the transport are impacted by the different processes that are occurring. And this fate and transport can, for example, impact the stability of the particles or whether they agglomerate and settle. So either are they impacting free swimming organisms or maybe on the seabed. We also saw with larger organisms as Daphnia and fish that it's much more complex with bacteria. So it's not only oxidation of the membrane and DNA and the plasma, it's also many, many other phenomena that are occurring with higher organisms until, of course, it reaches us. And so does anyone have a question? I think we got to about 12. So sorry that I took a little bit more time. Does anyone have questions? You can also save the questions for tomorrow because we'll continue to talk about the aquatic environment tomorrow.
Yeah. Hadas, you're on mute. You're on mute.
Oh, was I on mute only now?
Yeah. Now only. Don't worry.
Okay. Are you scaring me?
No. Nothing to worry. Actually,
it's the impact of those environmental nano particles on the toxicity. Just like, it's like. Whew.
No. You were just on mute just a minute back. That's it. I claimed as a host so that you got onto mute mode. Nothing to worry.
Okay. Thank you. But we're continuing this tomorrow. We'll go over the different nanoparticles type and their impact on the aquatic environment. And also talk about the impact on engineering design. So also you can keep questions for tomorrow.
Tomorrow, yeah, the same topic will be the same topics
not the same,
but the concepts will be the concepts will be spilled over for the next topic, tomorrow topics as well. Yeah, the mechanism, the toxicity. Yeah, I got it.
Yeah. Okay.
Yeah. Okay. If there are any queries, you can leave it in chat box. Otherwise, you can save it for tomorrow, so that you can address it to Professor Hadas. So.
Okay.
Okay. So let's meet tomorrow.
Mm-hmm.
Okay.
Yeah. Thank you very much.
Thank you.
Bye-bye.
Bye-bye.